Okay, so good morning, everybody, to this flat body symposium. Flat body symposium at CMD 2020 GEFES. My name is Leni Vascones. I'm together with Dima Efetov and Johannes Lischner. I'm one of the co-organizers of this symposium. We are going to start now with the talk. So please, for all the speakers, I will ask you to be strict on time. The invited talk are 30+8 in order to have some time to change the speaker, and contributed talks are going to be 15+3. So we are going to have 8 talks today. And so for the questions, we will, I will ask you to write them on the chat, just in order to be a bit faster, and I will read them. And it's my pleasure to start this symposium with an invited talk to presenting Jenny Lowe, who will give an invited talk on correlates. She is from Ohio State University, and she will talk about correlated insulating and superconducting states in Swiss bilayer graphene below the magic angle. So now, so it's please, Jenny.
Okay, yeah, thank you. Thanks, Lenny, for the introduction. Let me share the screen. Oh,
yeah, it is.
Just a minute. Huh.
Okay, so it was shared a bit moment ago.
Yeah, it was fine before. Okay, I think. Okay, you see my screen? Okay. Going to use a laser pointer. All right. Okay, so I'd like to thank the organizers for organizing the symposium. And I wish I could say that I'm so glad to visit Madrid, but at least I can visit in spirit. Okay, so let me move. I need to move this. Oh, I want to minimize icon a little bit. Are you still seeing my screen?
Yes.
Okay. Huh. That's just a minute. Sorry. That's okay. So yeah. So I am Jeannie Lau from the Ohio State University. Today I'll give this. I'll talk about this is fairly generic title, flat band and flat lens, but mainly I'll talk about work on superconductivity and correlated insulating states in twisted bilayer graphene below the magic angle. And I think I probably have a little bit of time where I want to tell you about recent work on Spinopic coupling, which is tunable by layer and electric field in the high mobility 2D semiconductor. And at the end, I'll tell you how this might be related with the Moires in this material. Okay, well, so you probably all have seen something very similar to this, so I'll be quick. This animation must have been seen over the past years. So we have, if you have say 2 layers of graphene, a small angle laid down at a small twist angle, and so you form this kind of you have this super lattice forming, and with a wavelength that's dependent on the angle. So this, I think, the story begins. I would say at least widely acknowledged by the field. That begins in 2001 by this now famous work by Alan McDonald's group, where they calculated the band structure of the Moires, of the twisted bilayer graphene. And so this is a continuum model where they predicted a magic angle of 1.05 degrees with a super flat band. So the flat band here is actually this blue line at 0 energy, and this is actually, at first I thought it's like the x-axis. Then you look closely, actually, okay, you see it's there's, you know, it's not completely flat, but it's, you know, but it's almost flat, right? So this have very large density of states at close to 0 energy, and this is, of course, is very unstable to electronic interactions. And therefore, so we expect interesting electronic phases can happen. And so since this prediction, many groups has worked on twisted bilayer graphene, so including some of these groups cited here. And I will say various interesting observations have been seen, but not anything, for example, very that will correspond to a high electronic interactions. Okay, so now, of course, so 7 years later, this seminal work from Pablo's group. Again, I still have trouble pronouncing Pablo's last name, so he'll just be Pablo. So in this 2 back-to-back Nature paper, where they have seen a insulating state near, okay, so let me back up a little bit. So in this twist bilayer graphene, they have observed 4 electrons or 4 holes per superlattice cell. And at this filling, so-called full filling, and the bilayer graphene, twisted bilayer graphene behaves as band insulators. When the twist angle is at 1.1 degrees and plus minus 0.1 degrees, and when you fill the band with 2 electrons and 2 holes per superlattice unit cell, then they observe an insulating state, which is attributed to a Mott insulator. Of course, now I think there's more thought on this, so now it's being called a correlated insulating state. When the system is doped away slightly from the half filling, for example, around this, for example, minus 1.8 and minus 1.4, where superconductivity is observed. And I think the superconducting state is that the observation of superconductivity is super surprising, and really has basically took the community by storm. And of course, now many groups have started doing this, and this is just a small fraction of the paper published over the past, actually in the 1 year after Pablo's first discovery. And now this field has expanded to include twisted double bilayer graphene, twisted monolayer on bilayer graphene, and ABC stacked trilayer graphene aligned to HBN, and twisted bilayer tungsten transition metal tricationides, et cetera, et cetera. So this is like super exciting field. And I'm sure this symposium will hear even more exciting announcements. Okay, so we joined the party. So we have made this work is led by my student Miguel here in a clean room outfit, and in collaboration with Matt Barker's group at OSU. And the theory calculations are performed by Fan Zhang at University of Texas, Dallas. Okay, so we fabricate the device for using the standard tear and stack technique. So we start with a large single monolayer graphene. You so come in with HBN and break off half of it, lift it, and then overlay on top of the other half. And so in this way, the angle, so we know the relative twist angle between the two pieces of graphene. And so here is a finished finished device image. So this is the data from the from this device, and so here we are showing the Landau fan, which is we're plotting a longitudinal resistance as a function of a magnetic field, which is the vertical axis, and the gate voltage, which is the bottom axis. Equivalently, we're labeling the filling factors on the top axis. So here 4 and -4, for example, correspond to having 4 electrons and 4 holes per unit cell. We see that we have a central direct point here, and then we have 4 very resistive insulating state. Actually, at 4 and plus at 4, filling factors 4 and plus -4, corresponding to the band insulators. And so from this charge density at which these secondary peaks occur, which is roughly 2 × 10⁻12 centimeter square, we can calculate a twist angle, which is 0.93 degrees. And we can see that the Landau fan converging to the central direct point, and each of them has degeneracy of 4, and so which is and also converging to the secondary direct point, also having degeneracy of 4. So this is consistent with agrees with previous reports. Okay, so now here we're plotting the line traces at different temperature, and these are taken at 0 magnetic field. So we see that, okay, so here we have this a central direct point, a secondary direct point on the side, and now between the primary and secondary direct point, we see this kind of the peaks here, which we attribute to the correlated insulating state at half filling. So this peaks occurs at about correspond to about 2 electrons per unit cell. And we can actually trace Landau fan going to these peaks, and this Landau fan have degeneracy of 2, also in agreement with previous data. Okay, so but what's interesting is that we actually did not expect, but we did find when we dope away from the half filling, so at roughly about 2.5 electrons per unit cell, we did observe superconductivity. As you can see here, as temperature decreases, the resistance becoming 0. So the superconductivity observed at the larger superconductivity pocket is observed when we have 2.7 electrons per unit cell, and if we trace the resistance as a function of temperature, and so we see this 2-stage resistance drop. So first stage occurs about 1.5 Kelvin, and then second stage occurs at between 0.3 to 0.5 Kelvin. We can always also see a critical current. So here we're plotting the voltage drop across the junction as a function of bias current and the gate voltage. So the center of the peak corresponds to about 2.7 electrons per unit cell. And we see that we have a superconductivity pocket, and the largest critical current is about 15 nanoamp. So this is kind of a small angle, and it's smaller than what was reported in Pablo's first initial work at the time. So at the time, we thought maybe if it's below 1 degree, we're not able to see superconductivity. But I think that's actually turns out to be the range of where you can see both superconductivity and correlated interslating state is larger than previously thought. Okay, so now we can actually see how they respond to a magnetic field. So if we're here, we apply a perpendicular field. So the superconductivity is suppressed actually by a very small field by about 40 millitesla. And if you apply a parallel, parallel magnetic field, it's suppressed by about half a Tesla. Okay, so now, so what else can we do? So what we actually did is extended the range of measurement to beyond the filling of the first band, meaning beyond having 4 electrons per unit cell. So here we're expanding it to actually roughly 14 electrons or holes per unit cell. And then actually, to our surprise, again, we actually see some additional features. So first we can, so what's pretty obvious is that we actually can see this additional size of Landau fan converging to basically 8 and plus 8 and minus 8, so have 8 electrons or holes per superlattice cell. And also we have, and also at 12 plus minus 12. And so we have, basically we have these fans converging to the 3rd and the 4th Dirac point. But what's the difference between the 3rd and 4th Dirac point is that we actually can see the, without the magnetic field, the ones at plus minus 12 electrons per unit cell have this resistance peak, but not the ones at plus minus 8. Although plus minus 8 ones at the 3rd Dirac point, well, you can see they becomes more obvious as the magnetic field is applied. Okay, so how do we explain this with this calculation performed by Fan Zhang's group at Gonzalez? So what they have used this basically the formalism from Madonna and Cochino groups, and they calculated the band structure for a twisted bilayer graphene with 0.93 angle. So what they confirm is that there is the band is actually still very, very flat, close to 0 energy. And also there is this higher bands crossing, actually almost looking like a Dirac point. And so that can explain the observation of the peaks, the resistance peaks, which are almost temperature independent at the plus minus 12 electrons per unit cell. So one additional feature, which is interesting, what we see is this sharp peak here, which only appears, which is a little harder to see, but it's actually becoming more pronounced with magnetic field. You can see a little bit down here. And this sharp peak occurs at plus minus 5 per unit cell, which is basically 5/4 filling. And this peak is actually have very strong temperature dependence. So as we increase the temperature, the peak actually quickly drops to almost almost nothing. Okay, so quickly disappears at 5 Kelvin. And so this we can, so here we're plotting some of the data points we have, the resistance as a function of 1/T. And so this Arrhenius plot gave us a measurement of the thermal activation of about roughly 1 Kelvin. And so if it's so it's fairly hard to see, but okay, we can trace some Landau fan going to this peak at 5/4 filling. And this Landau fan has roughly degeneracy of 8. And so this corresponds to the quarter filling of the higher band, not the not the lowest band, like close to equal to 0, but the higher band, and which is this band. Also kind of flat. This is from the band structure calculation by Fans group, and with a high density of state. And so it's a little bit it's different from the other quarter fillings that has been observed in the lower band, in the first band, in that the degeneracy is fairly large. So it suggests, which is 8, right, as opposed to the degeneracy of 2 at half filling and degeneracy of 1 at the quarter fillings of the lower band. And so this suggests approximate spin valley as full symmetry and perhaps another new emergent symmetry. Okay, so to conclude this part of the talk, so we have observed a superconductivity and the correlated insulating state in the twisted Ballet graphene with an angle of 0.93. And so this, so we suggest that we, instead of a magic angle, it's probably a magic range. And we also find that the electron interactions can dramatically influence the property of the Moires superlattices, even at small angle and high densities. Okay, so I guess I have just a little bit of time. Let me quickly go through this this second part of the talk, which is tunable spin-orbit coupling in high mobility 2D semiconductors. Okay, so just a quick introduction to spin-orbit coupling. So the twofold degeneracy of spin is protected by combining the time reversal symmetry and the inversion symmetry. So normally we apply a magnetic field, for example, that breaks a time inversion symmetry, and so that that creates spin. We know the spin splitting and gives us the well-known Siemens effect. But alternatively, we can also achieve spin splitting by breaking the inversion symmetry of the crystal, and that combined with a spin-orbit coupling, and so that gives us a spin splitting without an external magnetic field. So that's so spin-orbit coupling is a relativistic effect, and so the very briefly, it's simply just like electrons moving in an electric field, for example, between the from the crystal from the nucleus, experiences with an effective magnetic field in the rest frame. And so the spin-orbit coupling actually has a lot of, can find a lot of uses. For example, making spin transistors, qubits, spin-orbit torque, spin Hall effect, quantum spin Hall effect, etc., etc. So it's actually, even the term spin orbitronics has been used. Of course, everything is electronics these days. But on the other hand, there's always this love-hate relationship between physicists and the spin-orbit coupling, because spin-orbit coupling is really useful for doing all of this engineering, all this topological and spintronic phenomena and devices. But it also causes a lot of, can cause, for example, scattering, and can reduce the spin lifetime by significantly. And so, but now I think with the 2D materials, everything is very tunable. So what we find is that we can actually now tune the spin-orbit coupling with an external electric field, so that then everything can be gate controlled. So we can achieve a spin orbit, we can make regions with large spin orbit coupling where we want them, and region with zero or low spin orbit coupling where we want long spin lifetime. Okay, so the material we think is really great for this purpose is this Mitochondriolites. So it's family of layer semiconductors, for example, indium selenide, gallium selenide, etc. And so we're actually going to focus on indium selenide here. And so this material have a thickness-dependent band gap of 1 to 3 electron volt. And so high mobility has been demonstrated by Manchester group, and quantum Hall effect has been observed in high magnetic field. Okay, so I also want to say that this material is expected to be have a very flat band. Actually, the valence band is very flat, and so it's actually correlated state are also expected if we're able to dope to the highly hold dope the sample. Okay, so the device, we made the device by the standard transfer technique inside a glove box because it is sensitive to air. The device we studied ranges from bilayer to 10 layers. Okay, I think I need to speed up a little bit. Let me just say that we have Raycom mobility, have very nice data, and so here we show some data from 2-layer to 6-layer samples. Okay, so what surprising thing we find is that if we see the Schubert-de Haas oscillations that start at about 3 Tesla, or maybe 2.5 Tesla, but in some regions we actually see a node in the oscillation. So here is this line trace. For example, we have seen node in the oscillation, which suggests that they are basically a beating in the oscillations. And this we can actually also, if we do a Fourier transform of the data, here we show the two frequencies here, and we suggest that because Schubert oscillation is a measurement of Fermi surface area, so this suggests that we're actually having 2 different Fermi surfaces. And another observation is that this node in the oscillations can tunable by electric field. This is out of plane electric field, and so we can see that here the node goes to different places. Oh, whoops! I think. Oh, I'm missing a. Oh. Okay, I'm missing a slide. I don't know what happened to it. Okay, so what I'm trying to say is that this actually turns out to be a signature. This beating in the oscillation frequency is a signature for the Rashba spin orbit coupling. And the Rashba spin orbit coupling is basically you have a parabolic band and can be basically split laterally, and then you will have a the spins that actually goes in plane, and so one goes, for example, the inner band goes counterclockwise and the outer band goes clockwise. And so with this spin out and this spin, and how much this band split is controlled by the Rashba parameter, which is linearly dependent on the electric field. Yeah, so I'm missing a couple of slides. It's very strange. Okay, so let me just say that we can model the sample. We understood the data, and we can also model the sample by taking the Rashba spin orbit coupling into account, and can reproduce the data. And here, this alpha is basically this Rashba spin orbit coupling, and it is linearly dependent on the applied electric field. And here we are basically trying, in our model, we're trying to account for this crossings between the lambda levels, which is due to the crossing between the two spin orbit bands. And then when they cross, they produce this node in the oscillations. Okay, and in this sample, we have actually different atomic steps with different thicknesses. And so we're able to, in the same flake, we're able to study how the spin orbit coupling parameter varies as a function of layer number.
Hi, Gianni.
Yes.
We should speed it up.
Okay, yes, I am finishing up. Okay, so let me just, let me tell you, apart from this is a really interesting system, to just stay focused, stay on topic with this Moires symposium. I tell you one piece of experimental observation which we think might be relevant is that in a number of samples, in actually several samples, we observe these oscillations that are periodic in 1/b and density independent, as we can see here. So this we have this kind of fans, which are the Schubert-Haas oscillation. And on top of that, we have this very periodic oscillations, which is independent in independent of density. These oscillations actually persist to a high, this is a bilayer sample, they persist to actually fairly high temperature, here to 60 Kelvin. And so we can see the Schubert-Haas oscillation disappears quickly, but these oscillations persist. So we think it's not phonon related, and it's not related to Schubert-Haas oscillations. So we're still trying to figure out why this is the case, but it is possible that we have, I think at least one explanation is interlayer Moires existing in our system. And of course, this is just right now a hypothesis, and we're hoping to be able to, to provide more evidence for that, if that's the case. All right, so to summarize this part, we have seen gate tunable and layer tunable Rashba coupling, spin-orbit coupling in atomically thin indium selenide devices. And so I think this opens the door for indium selenide based spin orbitronics, and perhaps we can engineer Moires system based on indium selenide, for example, Moires spin orbit field, and maybe correlated states. Okay, so let me just say that, okay, Moore is different and Moires is different. I think this is a phrase I took from Karen. I think this is pretty nice, catchy phrase. And this is what I see as experimental challenges. Sample uniformity and reproducibility of the same devices from the same angle. And of course, I think one big challenge is the wafer scale twisted bilayer with uniform angle. Can those be grown? Can those be synthesized? So let me just acknowledge my group and also my collaborators. And thank you for your, thank you for your attention.
Okay, so thank you very much for this very interesting talk. So I see that there are already a few questions. Jose Pizarro asked, why is the plus minus 5/4 insulator a correlated one?
Why is, sorry, what? Oh, why is a correlated insulating?
Yeah. Why is it a correlated insulating one?
Okay, I guess it's a, let me try to see the data. It's a question like, why is it correlated? Well, it's insulating because obviously as the temperature decreases, the peak goes up very large. Why is it correlated right now? Of course, I think it just first unexpected from just simple band structure. It's not, you do not expect to see a, it's not, there is no band gap there. So I think, it's also, it shoots up very quickly, so the gap is actually fairly small. I don't think it's correspond to any, gap you would think from any single particle mechanism. So that's, and the band structure calculation indicates, it's kind of the second band is flat. So that's why we think it's correlated. I guess, yeah, it would be good to have more proof beyond that, but I think, yeah, for this, I think the evidence for its being correlated is, I think it's there.
Okay, thanks.
Mm-hmm.
From Umesh Gorai, so he asked, what are the major differences in the 0.3 degrees transport data with the previous 1 degree transport measurements by Cao et al.? So which are the differences in the transport between this 0.93 degree and the one by Pablo Jarillo? Yeah.
I don't know if there's any real difference. Yeah. Yeah, but I think since then, I thought Pablo's group also observed superconductivity in samples with angles smaller than 1 degree.
Okay, thanks.
Yeah.
Johannes Lesner asked whether you can fabricate twist indium selenium bilayers using the shear and stack method.
I believe we can. Yeah, so that's something we are trying, but I would say, well, one thing is that monolayer indium selenide is fairly difficult to obtain. So I think that's, but we have made twisted basic bilayer, well, twisted, that would be called twisted double bilayer. I think that can be done. But sadly, I don't have any, really good data to show yet.
Okay. So I myself have a question.
Mm-hmm.
For the half-filling insulators or correlated states, so so normally I associate an insulator to resistivity which increases when I decrease temperature. So I see that you have a peak, so a resistive state, but
yeah,
now it seems to me that the dependence on temperature is associated to a metallic state, not to an isolating state.
Yes, I agree. I think if we're just based on solely this data, you will suggest a metallic state. I guess we think it's just because you can see the superconducting state is kind of almost starting to take over. So we think that there's some sampling homogeneity and percolating paths that cause the resistance to actually decrease instead of increase as temperature decreases. And I think this is also consistent with I think some other work, for example, from Columbia Group.
Okay. So I do not see more questions. So then I thank Gianni again. So I'm going to clap for all of you because so you cannot. And then so thanks. So now if I will ask our next speaker, we start with the contributed talks. So our next speaker is Tero Hikila from University of Jyväskylä, and he will talk about flat band superconductivity into its bilayer graphene. Okay. So.
Thank you.
Yeah.
You can, I guess you can hear me.
Yes, we can hear you. Yeah.
Thanks for the opportunity to give this talk and tell about our work. I will tell you about flat band superconductivity in twisted bilayer graphene, and this work is based on 3 theory papers which are listed here, 3 PRBs. And it's also based on Teemu Peltonen's PhD defense, PhD thesis, which will actually, the defense will take place in 2 days in Jyväskylä. I often show this picture that is on my first slide. This shows Jyväskylä, which is in the center of Finland. The city center is on the left, and then I'm actually in the building on the right. And actually, I'm giving this talk now from that building. So this is the unusual case. I'm showing sort of a number of results which are based on numerics. You can actually test this numerics yourself by downloading the codes. The codes are available for download at this address that you can see. Actually, I don't see my pointer, so I will just go without a pointer.
Okay.
Okay. So since my topic is flat bands, I need to explain what I mean by flat bands and why they are different from ordinary Fermi surfaces. So the 2 first pictures that we see on this slide are the standard picture of electron systems. We have band insulators, we have metals. And in metals, we have Fermi surface physics. So typically, the Fermi surface physics means that any transport observable or any correlated state takes place close to, at energies which are close to the Fermi energy. And the Fermi energy is the largest energy scale. This is in contrast to, for example, semimetals like graphene, where we have a band crossing. And if the Fermi energy is at the band crossing point, the physics is quite different. But the main topic of my talk is the flat bands, and you can kind of, as a theorist, you can have a picture of an ideal flat band, which is on the left, on the bottom. It is either a flat band that is connected to the rest of the states with dispersive bands, or just an entirely flat band. In practice, this flat band has some finite bandwidth. So this is shown on the right. And the rightmost picture is the one which you actually get for the Moires lattice in graphene. However, if the energy scales of your interest, let's say for superconductivity or other states, are large compared to this bandwidth, then you can actually go back to this limit of ideal flat band. It doesn't really matter which one you consider. Okay, majority of the sort of theories for the properties of superconductors are based on mean field theory, on BCS theory, and their superconductivity is described by a self-consistent order parameter, and this order parameter brings out the gap to the dispersion, which can be written by this quantity delta in the dispersion. And in the presence of this gap, you can write the free energy of a superconducting state so that there is a condensation energy plus the change in the quasi-particle kinetic energy. And if you look for the minimum in this free energy, this minimum actually provides you a mean field value for this order parameter delta. And from the minimum, you get the self-consistency equation for the delta. And the self-consistency equation depends on this normal dispersion. Okay, so let's look what happens to the results of the self-consistency equation depending on the dispersion. So first, if you have a Fermi surface, what this means that the density of states is almost constant near the Fermi energy, and therefore you can actually kind of take it out of the integral. And but in this case, the superconductivity is described by something where there is an ultraviolet divergence, which you need to cut off, and or logarithmic divergence. And once you then plug this in, you solve for delta. What you get is an exponential relation between delta and this cutoff energy. So delta equals this cutoff energy times some exponent. And basically, this exponent has a very small value. Typically meaning that the delta is actually much more than this cutoff energy. So superconductivity is kind of exponentially suppressed. It shows up at low temperatures. Now, if you plug in a linear dispersion, so if you consider this semi-metal case, this is kind of the worst case scenario. the smallest density of states. What you find out is that you don't get superconductivity below certain critical coupling strength. So this sort of Cooper instability that is valid for metals is closed in the semi-metal case. But this is in contrast to flat bands. If you assume that now this delta is large compared to the energy for some finite bandwidth of the momentum space, you get actually linear scaling between delta and the coupling strength. And this linear scaling comes with the size of the flat band. And okay, this is in pictures a bit more. So on top you see, okay, it would be nice to see my mouse, but I don't see it. Let's see if I can. Apparently it doesn't work, but okay, it doesn't matter. So on top you can see the kind of pictorial representation of what I just had. You have 3 types of dispersions. If you have a semi-metal that has a Fermi energy, but your Fermi energy is outside the band crossing point, then it also the physics is like the Fermi surface case, and you can solve for the critical temperature, and you get this exponential dependence. And okay, and then you can do a little bit more sort of detailed theory. For example, if you consider a certain mechanism for superconductivity, electron phonon mechanism is the most usual one, and then you can describe the superconductivity with this Macmillan formula. Now, this does not hold for flat bands. In the case of flat bands, you get that this critical temperature is actually proportional linearly to the coupling strength times the flat band size. You can also there, however, do this Eliashberg theory, which we did this a couple of years ago, and then you can kind of get corrections to this linear scaling. And actually this theory is a competition between superconductivity and Coulomb-mediated effects such as magnetism, which would actually lead to a correlated insulated state in such a system. But in my talk, I will only focus on superconductivity. Okay, so this was the theory for the order parameter of superconductivity in field theory. But then superconductivity also requires that supercurrent can flow. So and for that you need to study supercurrent density, which is then given by sort of the phase gradient times the superfluid weight, ds. And in conventional BCS theory, the superfluid weight is proportional to the particle density divided by the effective mass. Effective mass diverges for a flat band, and therefore it seems that actually the particles are stuck and they cannot carry supercurrent. However, also this is not quite true in flat band case. If you have multiple band situation, the superfluid weight is the sum of this conventional contribution that is proportional to the inverse of the effective mass, plus then a geometric contribution that depends on the metric of the eigenstates. And it basically describes the non-localization of one-year functions of the flat band states. And but also from this superfluid weight, you not only get the supercurrent, but you also get the Berezinski-Kostelis-Taulos temperature by this formula that is on the bottom of the slide. Typically, this is smaller than the mean field TC, and this is actually the temperature at which the resistance goes to 0. Okay, so we have applied these ideas for twisted bilayer graphene, and we basically took the microscopic models of from these papers of Lopez and Santos and Suarez Morel to describe the normal state dispersion. The basic idea is to start from describing the two coupled layers, find out the superlattice, let's say Brillouin zone, and describe the hopping coupling the different elements of the superlattice reciprocal lattice. Okay, and once you do all this, if you do it properly, you find that let's say you can find the eigenstates of this Hamiltonian, and then you can just plot them as a function of the transverse momentum, and you find this flat band at the magic angle, which is now this 1.08 degrees in this model. the density of states is not entirely flat. There is a finite bandwidth, which in here is roughly of the order of 3 milli-electron volts. This is not exactly the extension of the entire band, but this is the size where the density of states is sizable. We have also used another approach, which is kind of a renormalized tight binding approach. The issue is that at the magic angle, the superlattice unit cell has around 10,000 atoms, which means that the tight binding Hamiltonian is kind of hard to operate. So to describe superconductivity, we have kind of renormalized the interlayer coupling to get the magic angle higher, and then therefore the superlattice a bit smaller, having a bit smaller unit cell. So, but we compare these two methods in here. To describe superconductivity, we then plug this Hamiltonian into a Bogolian equation and solve for the eigen values and eigenvectors. And then we can get the self-consistency equation by assuming that there is some interaction. Okay, and so this we did a bit more than 2 years ago, and there initially people thought that the superconductivity must be coming from some unconventional mechanism by electron-electron interactions. But we pointed out that also electron phonon actually is a viable mechanism for superconductivity because of the flat band scenario. Okay, no, electron phonon mostly leads to a local pairing, and therefore S-wave superconductivity is dominant one. We also considered some non-local pairing that does not have to come from electron phonon coupling. And then we also calculate the superfluid weight, and in the following I show some results of these calculations. So here, remember, I only concentrate on the superconducting state, so the correlated insulating state is not inside. So one thing first, you can find out the order parameter, and you can find that it's strongly inhomogeneous. It depends on position, and this is because of the fact that the flat band eigenstates are inhomogeneous. The delta, the superconducting delta depends on doping. There is some critical doping strength where you suppress superconductivity, and this is kind of similar to experiments. But here we don't see the correlated insulating state at the center of this doping diagram. And the exact values depend a bit on this, how large a coupling strength we put in the theory. You get delta versus this coupling strength, which is actually pretty close to linear beyond a certain critical strength. And this critical strength is actually sort of related with the fact that if you look very deep into this dispersion, it looks like a semi-metal. Yeah. Okay, but you can also study, let's say, the delta versus the angle for different coupling strengths, and this is what you see on the right in this slide. So you can see that close to the magic angle, superconductivity should appear, and elsewhere it disappears. Yes, okay, beyond this, you can study the Berezinski-Kosterlitz-Talos physics, the BKT temperature that you obtain from this first by calculating the mean field order parameters, and then calculating the superfluid weight from there. You get kind of a similar linear scaling between the BKT temperature and delta. And okay, here I show on the right top, I show the BKT temperature as a function of doping for these different types of models, either this direct point method or the renormalized Moires method. And you can see that there are some differences between them, but overall they show pretty similar behavior. One thing is then to ask the question whether this the superfluid weight is given by this conventional or quantum metric contributions. This depends on the size of the gap. So if the gap is roughly about half of the bandwidth of this flat band, then you start to get more and more of this geometric contribution to the superfluid weight. Okay, now you can also plug all this and compare it to experiments. these are curves that I made for this talk, taking, and actually with the help of Teemu Peltonen. So taking this data for BKT temperature and then comparing them to two experiments, one from Andrea Young's group on the left and one from Harila Herrero's group on the right, and as a function of angle. And you can see that the error bars in their experiments are pretty high. There's also a little bit of caveats and when trying to compare this, but you get at least rough idea that it seems to work pretty well. And from these comparisons, anyway, you get you can fit the size of the coupling constant, and you can then get some values for the TCs of the midfield TCs, let's say. And this basically tells that the twisted bilayer graphene is on the verge of this sort of strict flat band limit where delta is actually large compared to the bandwidth, and where you cannot use any Fermi surface arguments to study superconductivity. Okay, so we also studied the nature of the pairing, and what we get is that the.
Sorry, you should be.
Yeah, I should be wrapping out. Yes, so I just mentioned that we've kind of described both nematic order and S-wave order, and then this shows up in the form of this superfluid weight, and this can be measured actually with AC techniques, and this is what this suggests. Okay, so I will come to kind of conclusions. We found out that flatband superconductivity is a viable sort of approach to studying superconductivity in twisted bilayer graphene. But the issue here is that the flatband size actually limits the delta, and flatband size is actually the size of the superlattice Brillouin zone in twisted bilayer graphene. And this is quite small. So, but even that gives you a TC of a few Kelvin. So if there would be a way to get bigger flatband sizes, you would shoot much higher. You should be able to get much higher critical temperatures for them. Okay, I guess I'm out of my time, so I will stop here. Thank you for your attention.
Okay, so thank you. Well, so please write your questions in the chat. I will start. Okay, so there is one here. Notes I will have planning. I was going to start. So there is one question from Umesh Gorai. So it's asking, why is there a particle hole asymmetry in BKT temperature for twisted bilayer graphene?
Thanks for that question. So I guess you're referring to, for example, this picture on the right, where the particle hole asymmetry in actually in the theory depends on the model that we used. So this Dirac point model does not seem to capture any. It seems to actually rely on a symmetry that leads to particle hole, complete particle hole symmetry, whereas this renormalized Moires sort of shows a slightly asymmetric dispersion, and therefore this BKT temperature can be a symmetric function of the doping. And this, I believe, is related with a small breaking of the inversion symmetry in these models of coupled two layers. So this is kind of a minor breaking of the symmetry, and then this inversion symmetry breaking leads to a lack of particle hole symmetry.
Okay, so I have one question. So I have seen that you estimate your delta of order 2 milli-electron volts, if I'm correct.
Yeah.
Yeah, and so for there the conductivity. So it has contribution from other bands, right? Not just from the flat band.
The flat band regime, yes.
Sorry?
Yes, everything at this flat band regime. Yes, I mean, we have calculated the superfluid weight also depends on coupling to higher order bands, which we have included. But the most relevant contributions, of course, come from the flat bands. Okay, so at this value of the, it comes mostly from the flat bands. Okay, yeah. Thank you.
So then, well, so if there are no further questions, then we thank Tero again. And then, so we go to the next speaker. So next speaker is Tommaso Zea. He is from INDEA Nanociencia in Madrid. And he's going to talk about band structure and insulating states driven by the Coulomb interactions in Twist bilayer graphene.
Hello, everyone. Thank you for giving me this opportunity of having this virtual talk in Madrid. And I'm going to talk about the role of the Coulomb interaction in Twist bilayer graphene, which is a work done in collaboration with Paco Guinea in Madrid, and recently published in Physical Review B. So, as we know, since the discovery of superconductivity and insulating behavior in Twist bilayer graphene, close to the magic angle, this kind of system established a new paradigm in the study of the quantum many-body phenomena. Experimentally, there has been observed alternating superconducting and insulating states at integral filling of the conduction band. In particular for 0, 1, 2, 3, and 4 electrons or holes per Moire unit cell, including the spin valley degeneracy. So let me give a fast overview, a rapid overview of the general features of the Moire potential and fast bands in Twist bilayer graphene, close to the magic angle. What happens? When we rotate two layers of graphene by an angle which is close to 1 degree, we generate a Moire pattern of alternating stacking regions with a period of approximately 13 nanometers, which means that we have approximately 10,000 electrons per Moire unit cell, and this hinders state banding and or ab initio calculations. In addition, the hopping between pz orbitals localized at the carbon atoms in different layers gives rise to a local interlayer potential, which is periodic in the Moire unit cell. And this promote the use of the effective continuum model, which represent a much, let's say, a much easy tool as compared to the tape banding calculation. Now, close to the magic angle, this local potential gives rise to almost flat block bands close to charge neutrality, with a bandwidth which is very small, more or less 5 MeV, depending on the angle. And this gives rise to a strong Van Hoff singularity at the charge neutrality point, at the Fermi level. This means that at the magic angles, the hopping between electrons in opposite layers quenches their kinetic energies, and this inevitably enhances the role of the electronic interactions. Now, this physics gives rise to several challenging theoretical issues. For example, the first one is to understand if this kinetic quenching is enough to explain the observed states in the experiments, what kind of symmetry breaking are taking place, and finding a way to study theoretically and systematically the effects of the electron interaction in Twist bilayer graphene. In particular, here we focus on this last point and study the role of the Coulomb interaction. Now, let me mention why the Coulomb interaction are expected to be relevant in this system. We can perform a raw estimate of the interaction strength by putting numbers. That means for the 13 nanometers for the Moire period, and the electric constant, an electric constant ranging from 4 to 10, which is compatible with a substrate of hexagonal boron nitride. and we realized that the interaction strength ranges between 20 and 50 MeV, which is small but much larger than the, which is in absolute small, much larger than the bandwidth, the width of the mini bandwidth. So far, there have been many theoretical works attempting to study the role of the Coulomb interaction in the formation of the correlated insulating states in twist Ballet graphene. And there have been proposed different types of many body correlated states, breaking different kind of symmetries. What we have done has been to perform a self-consistent R3-Fock approximation within the continuum model of the twist Ballet graphene. As everybody knows, the R3-Fock approximation implies the approximation of the interacting of the electronic interaction by means of two kinds of potentials: a local potential, which is the R3 potential, and the Fock potential, which is non-local in space. Now, these psi are electronic field operators, and Vc is the Coulomb potential. These two kinds of potential define the self-energy of the electrons, and what we have done has been to compute this potential self-consistently and the resulting band structure as a function of the electronic filling. What we found, for example, at charge neutrality, is that while, of course, while in the absence of interaction, the bands display a Dirac point. This Dirac point is gapped out in the presence of interactions, so that at charge neutrality there appear a spectral gap, which we estimate to be around 5 MeV, which is a small gap, but however it is comparable to the non-interacting bandwidth. In this sense, we can talk about a weak insulator. Now, let me mention the type of symmetry breaking that we report related to this gap opening, and in particular we report the breaking of the sublattice symmetry, also called C2T of pristine graphene. As you can see in these figures, here I show the charge density in the Moires unit cell, computed in different sublattice and layer. So that in the bottom panels, you can see that I show the charge density in the two layers, rho 1 and rho 2. And we can see that the charge density is equally distributed in the two layers. On the other hand, in the top panel, you can see the charge density computed in different sublattices, sublattice A and sublattice B, let's say. And we can see that the charge density is mainly accumulated only in one of the two sublattices. So that this show the kind of symmetry breaking associated to the opening of the gap at charge neutrality. Now, if we move away from charge neutrality, we can see that the red bands are completely reshaped depending on the filling of the conduction band, and in particular the spectral gap closes as we move the Fermi energy away from the position of the Dirac cones. So that, for example, here we see that when the electronic filling is 2, which means 2 electrons per Moires unit cell, the C2T symmetry is completely restored, and the gap, the insulating gap is closed. Now, this picture of course, can describe the appearance of insulating behavior at charge neutrality, but not at other integral fields of the conduction band. However, what we can do is to break the spin valley degeneracy of pristine monolayer graphene, and repeating the same time of calculation, we can obtain additional insulating state just at integral filling of the conduction band in agreement with experiments. So what we do to break the spin valley degeneracy is to polarize the ground state let's say depending on the spin and valley, and in general we polarize it so that there are the band structure accounts for two set of degenerate bands, and these bands differ each other depending on their degeneracy. So that, for example, here we can have on the left a configuration that we call 2+2, which means that we have two sets of bands. Each set is two times degenerate, and of course the two sets of bands are one set is a high occupancy band, a set of high occupancy band, and the other set is a low occupancy set. And we find, unfortunately, I have no time to show the band structure that we obtain for each of these configurations as a function of the filling. However, we find that a spectral gap opens every time that for filling such that one of these bands shown above is half filled, and then so that once we have analyzed the band structure of the different polarization arising in each different polarization of the ground state, we compared their their ground state energy to see which of these configuration is more stable, and we find that in general each of these configuration is these configuration are very close in energy. They are almost degenerate, and this implies that the nature of the ground state can be very, and of course of the insulating state can be very sensitive to the environment. For the parameters that we used, which is the electric constant of approximately 7, which is let's say enough in agreement with the type of substrate that are used in the experiments, we found that the configuration that we called 2+2 is almost always stable, but closer to integral filling -3, -1, 1, and 3. Now, this can be better seen in these final figures, which shows the values of the density of state at the Fermi level as a function of the electronic filling, so that we can see that every time that we have a suppression of the density of state, we report an insulating state, the presence of an insulating state. This happens for filling equal to more or less -2, -1, 0, 1, 2, 3, but for -3. And so that -3 is the only integral filling where we don't find insulating behavior. Now, these insulating states, however, can take place in different polarization of the ground state, which is depicted by this colored stripe, so that in general we find that the most stable configuration in a wide range of filling is the one called 2+2, which means that we have two set of twofold degenerate bands. And however, this picture, these findings are in quite agreement with the so-called cascade of phase transitions that are being observed and reported recently in a work by the group of Pablo Carrillo-Herrero. And so I think I have concluded, and let me overview the conclusions, so that we have studied the effect of the Coulomb interaction on the band structure of the twist-barrier graphene within the R3-Fock approximation in the continuum mode. We report the breaking of sublattice symmetry, also called C2T, of monolayer graphene at all filling of the conduction bands, which strongly suppresses the Fermi surface and favors the formation of insulating states. And we found that the ground state is almost always spin valley polarized, according to different polarization. But we remark that the nature of the ground state and of the found insulating states can strongly depend on the screening from the environment. So I concluded, and I thank you for the attention.
So thank you, Tommaso, for the talk. I see that there are several questions already. So let me start. So is there any experiment? So this is from Jose Pizarro. He asked whether is there any experiments which could be done to differentiate the spin and valley polarized configurations?
Yeah, let's say that the spin and valley polarization can be in principle differentiate each other by depending on which we apply a perpendicular or a parallel magnetic field. So that in principle, for example, if we apply a parallel magnetic field, a perpendicular magnetic field, we may identify a peculiar spin polarization by means of the Zeeman effect. On the other hand, the splitting on the Landau levels could justify the valley polarization.
Okay, so thank you. Johannes Lechner asked, is there an intuitive explanation for the energy ordering of the various spin valley or orderings? Why should I expect that 2+2 is lowest in energy?
This is a very good question. We don't have let's say an intuitive explanation, also because this apparent stability of the 2+2 configuration depends on the environment. So that if we change the environment, it's possible that, for example, the non-polarized configuration becomes stable, depending on the filling. So that I cannot give an explanation, an intuitive explanation of this behavior.
Okay, thanks. And Tero Hikila asks, could you add the electron phonon and Elias-Verret scheme? This will double the size of your Hamiltonian and imply an additional self-consistency equation.
You mean adding electron phonon?
Yes, that is.
Yeah, it's doable, but in principle, yes.
Okay, thanks.
You're welcome.
So if there are no further questions, so I thank Tommaso. And we go to the next speaker, So the next talk is going to be presented by María José Calderón from Instituto de Ciencia de Materiales de Madrid, and she will talk about interactions in magic angle twist bilayer graphene. Is there any problem? Okay. I think you are muted. Okay.
Okay, sorry. Okay, can you see my screen?
Yes, we can see
Yes,
it.
okay. Well, so thank you very much for this opportunity for telling you this work that I have done in collaboration with Lenny Vascones, that you all know very well because she's the chair of the session. So what we want to study is what is the origin of the correlated states in TBG upon doping. I mean, the question is whether this is mode physics or there is some standard mean field symmetry breaking. In order to do this, we need to have a suitable model to study the interactions that we know, I mean, that we have all these correlated states, and we need this model in order to study this. Okay, so one thing that it's clear is that the correlated insulated states appear at the interior filaments of the Moire unit itself. And this seems to suggest that an effective biennial model for the Moire lattice is appropriate to study interactions. There have been different effective models proposed, in particular some models only for the flat bands with 2 orbitals per Ballet. These ones can include explicitly, they cannot include explicitly all the symmetries in the system. And they also have a peculiar shape of the orbitals that I will remind you later, where there is a high probability density of the wave function away from the center of the wave function. This can lead to problems in the calculation of the interactions, we wanted to go beyond and see what we could do with other kind of models. And in particular, the problem of the symmetries can be overcome with including higher energy bands. And one of the models that have been proposed is one with 8 orbitals per Ballet by Stephen Carr and co-workers. And this is the one that we're going to use. And I think that you will understand why we like this model, particularly for these interactions, to calculate the interactions and include them in TBG. Okay, so this model is based on a Biennial function construction that fits relaxed TBG. Okay, so the system we're starting with is relaxed. And it includes explicitly the symmetries of the system. And we can see here that it is valid for a wide range of angles, twist angles around the magic angle. The 8 orbitals are centered at the 3 TBG symmetry lattices. This is already different from the 2 orbital models. So we have the 3 symmetry lattices are the triangular lattice, that is marked by the positions of the AA regions, the orange points here. Here we have 3 orbitals, 2 with a p symmetry, 1 p plus and 1 p minus, and 1 with an s symmetry. Then we have an hexagonal lattice that is marked by the regions A, B, B, A. So these are the green regions here. And there are 2 orbitals with a PC symmetry. And then we also have a Kagome lattice that is sitting at the domain walls between the 2 kind of regions, AA and AB. And there we have 3 orbitals with S symmetry. Okay, so what we see is that the orbitals are centered at these symmetry lattice points, and their shape of the wave function, I mean the probability density of the wave function has the maximum around that point, not far away, like in the 2 orbital model. Okay, so this Biennial construction in this 8 orbital model is done in a way that you guarantee to have a maximum weight of the AAP orbitals which are, I remind you, the ones that are in the triangular lattice on the flat bands. But we have also some small weight of the other orbitals, but only at gamma. Okay, so this would be the kinetic, I mean, with this model, we can study or have the kinetic part of our Hamiltonian. This is our tight binding. And in order to include the interactions, we need to calculate these U's. So to calculate this U, we have to do these integrals that involve 4 operators in R and R prime. So we have to integrate in R and R prime. And A, B, C, and D can be any combination of the 8 orbitals that you can imagine, but not all these terms are going to be important. The thing is that we have to take into account that because this is a multi-orbital system, we are going to have both intra-orbital and inter-orbital interactions, and because the biennial functions are large, I mean, compared to other systems, then interstate interactions can also be important, so we are going to study those as well. Okay, so the kind of terms that are more, that are expected to be more important are the density-density terms that corresponds to B equal to C and A equal to D. The exchange terms and the assisted hopping terms have been considered or have been found to be very important in the 2 orbital models. So we are also showing what we get from that. For exchange terms correspond to A equals C and B equal D, and the assisted hopping terms correspond to A equal D and B different from C. Okay, so just to remind you how the 2 orbital model wave functions are, they have the center at the AB points of the lattice, while their maximum probability is on the AA points, or AA regions, rather. Okay, you can see that the results are going to depend on epsilon, which is the dielectric constant of the system. The results that I'm going to show you now are done for epsilon 12, which is an estimate that we have done by comparing our Hartree results that I will show later with some atomistic Hartree results by the group of Johannes Lichner. So we estimate this epsilon 12 in vacuum and epsilon 15 if we had HVN encapsulation. Okay, so these are the results for the intra-orbital on-site density-density interactions. So the different colors, the orange is for the AAP orbitals, the ones that dominate the flat bands. The red is for the AAS orbitals. And then these are for the domain wall orbitals, and these are for the hexagonal orbitals. We can see that the highest is the one that corresponds to AAP, and it doesn't depend much on the twist angle, and this is because it's a relaxed model. We're starting from a relaxed model, and in a when you have relaxation, the AA regions are smaller, they contract, and it has been seen that for twist angles below 2 degrees, they don't change much. Okay, so we see that this interaction is scaling with the size of the AA regions, and as it doesn't change, then it is more or less constant. Sorry. Okay, but in order to know whether this interaction is important or not, we have to compare it with the bandwidth. And here we show the density of states weighted on each kind of orbital, and we can see that for the AAP orbitals, we have a very narrow bandwidth. So U over the bandwidth is going to be the largest for AAP, while if we look at the other orbitals, we can see that we have a quite wide bandwidth, and then we expect that even though the density-density interactions are sizable, maybe they are not so important when we study the correlations when we compare them with the bandwidth. I just want to stress that we have this peak here that is something that I mean would be related with the results that Jenny Lowe had been showing us in the first talk. Okay. So we also looked at density-density interactions between different orbitals and also for different distances. So lambda is the Moire unit length, and we can see here that we plot everything, all the values that we got, and we can see that the results for the interactions fit a 1/r curve once the distance between the atoms is over lambda over 2. So this is what we would expect from point-like charges, and is something like more conventional than what the two-orbital model would give with a much larger range interaction. Okay, about the on-site exchange, the results are much smaller. So we have very low values for this exchange, on-site exchange interaction. And this comes because of the complex biennial wave functions that remember that we have an envelope part of the wave function and a block part. The block part changes very rapidly at the atomic scale. So for instance, if you calculate the exchange between different valleys, these oscillations will probably will mostly cancel the interaction, but we also have complex phases in our wave functions. That means that, for instance, this on-site exchange between AAP orbitals in the same valley also have a very small value because they compensate. There is an interference, a destructive interference. The largest would be between AAP orbitals and the AAS, but the AAS orbital has the maximum weight away from the Fermi level, so we don't expect it to be important because most probably we won't have spin polarization. Okay, also the intersite exchange and assisted hopping that, as I said, are very important in the modelization with two orbitals, are very small here. Okay, so, and this is basically due to the weak overlap of the Biennial functions in the different unit cells. But I mean, they're still there, but it seems that they are not so relevant compared to the other ones, density ones. Okay, so so far we haven't included the fact that most of the times, or always, we have a gate or two gates nearby. This is what you need to make the experiments and take measurements. And there has been a lot said about that gate screening can change the interactions and how they can affect the phase diagram. So we looked at the effect of a gate, of a single gate that would be this solid curve, and two gates. This is the dash curve, both for on-site and first neighbor intersite density interactions between the AAP orbitals. This is the largest interaction that we have found, and we have seen that if you put your gates at a distance equal to lambda, which is the characteristic Moire unit length, the Moire length, sorry, what we see is that for this distance of the gates, the on-site interaction is reduced only by 11% or so, while the first neighbors are reduced by a 40%. So this means that the gates are actually affecting much more the farther away interactions than the on-site interactions. And in fact, in order to suppress the on-site interactions significantly, we should put our gate distance, our gates at a distance of about 4 or 5 nanometers or less, which is quite small. Okay, so now that we have our interactions, we can plug them in our Hamiltonian, and the first thing that you can do is mean field calculation, a hard tree calculation. That is something that other groups have done already, but we have done it with this model that we, I mean, this model proposed by Stephen Carr plus the interaction that we have calculated. And what we find is that there is a deformation of the bands. So here we are doping with electrons, here we are doping with holes, and the black curve is without doping. And we can see that there is a deformation that affects basically the gamma point, because the hard-tree potential is measured with respect to the AAP, or is calculated with respect to the AAP orbitals. So we have that this deformation is occurring here, and this is something that has been observed, that has been calculated and observed in other HAR3 works. But the thing is that here we need we know what is the origin of this deformation here, and is that this HAR3 potential is different for the different kinds of orbitals. So it's different for the ones on the triangular lattice, and the ones in the hexagonal, and the ones in the carbonyl lattice. So with this, oops, sorry, I conclude. We have calculated the interactions in the 8-orbital model for twisted bilayer graphene. Remember, this is 8-orbital model per Ballet. We have found small on-site and inter-site exchange and assisted hopping terms. This is unlike what has been found in other models that many people are using, like the 2-orbital models. We have found that the largest terms are the density-density interactions, and they have a conventional shape, like with 1/r behavior for long distances. We have also seen that the screening of the AP on-site interaction would need gates very close to the twisted bilayer, while the other interactions are screened even if your gates are at a larger distance. And we also have seen that the dope-independent bands at the HAR2 level reveal the presence of orbitals that are not the AP at the flat bands. So now we think that we have a good starting point for studying correlations in the twisted bilayer graphene, and I hope that I have convinced you of this. Thank you.
Okay, so thank you very much. Is there any questions for Maria Jose? Everything is clear? Oh, so there is one question from Pablo San Jose. He asks whether the model is adequate also for strong deformations at very small angles.
You mean the tight binding model? The tight binding model is it has been used between 0.6 degrees and 1.3, and they can fit quite well the bands.
Sorry, Pablo, what do you mean deformation? Okay. Are there questions? Okay. So then there are no more questions. We move to the next speaker. We thank Maria Jose.
Thank you.
And so the next speaker, so the next talk is an experimental talk. So it's next speaker is Simone Lisi from Geneva University, and he will talk about evidence of weakly dispersive bands in twisted bilayer graphene from nano-ARPEs.
I'm trying to share my screen. I should succeed at some point.
Okay. So
you can't see my screen, right?
Yeah, now we can see the screen.
And now you should be in presentation mode, right?
Now it's in presentation mode.
Okay. Thank
you. In my talk, I would like to show you our latest results on the investigation on band structure of twisted bilayer graphene with ARPEs. And in particular, I would like to focus on the challenges posed by producing samples suitable for this technique, so for angular result Photoemission spectroscopy, and what we observed on these kind of samples. I would like to start with a brief introduction, which will be real quick thanks to the previous speaker that covered most of the things I wanted to show you. So in particular, I wanted to start with addressing how we can calculate the band structure of crystals in a very simple way, which is with tight binding. For example, if we take a linear chain of atoms. All we need to do is to account for electrons hopping from one side, atomic side, to the other this way, and we can calculate the band structure of the system. Now this hopping parameter T is mainly responsible for the bandwidth here. And then what happens is that this very simple model is extremely successful in describing the phenomenology of many materials, in particular in predicting whether a material will be conductive or insulating depending on the filling of these bands, which means that we would expect insulating states when the bands are completely filled, or metallic behavior when the bands are partially filled. Now, this method is very simple, it's quite successful, but sometimes it fails spectacularly. And this is because for some materials, we can observe an insulating behavior when bands are half filled. Now, this is because in the previous Hamiltonian, we ignored the term, which is the on-site Coulomb repulsion among electrons, which means that we ignore the fact that if an electron is occupying an atomic site, another electron might have a hard time hopping there. And this is a legit approximation in many materials, because this hopping parameter T, which is the kinetic term, is much higher than this on-site Coulomb repulsion. And this is why many materials can be described this way, but sometimes these two terms are comparable, and then we can observe what is called Mott insulator physics. And in the previous talk, we saw that in twisted bilayer graphene, the picture is a bit more complicated, but the flavor is, this can give us really the flavor of what's happening here. Now, if we apply this same model to graphene to calculate the band structure of graphene, what we know is that with tight binding, we can calculate a single layer graphene band structure that will look like this at the Fermi levels, with two converging Dirac cone at the touching here at and the Fermi level will lie exactly at the tip of these two cones. And what happens when we put two graphene layers on top of each other and we twist them is that if no interaction is established between the two layers, we just expect to see something like this. So two replicas of this band structure with no substantial changes. But then if we trigger an interaction, the two layers start to talk to each other, and some gaps can be opened where the bands are crossing. And this effect can become particularly dramatic when a certain relation is matched between the interlayer interaction and the twist angle, which is responsible for the value of this k theta, which is the differences between the k vectors of the two graphenes. And for certain angles, what it has been shown is that the bands can become as weakly dispersive as being completely flat. And the flat band means that the kinetic energy term in this band can be comparable even with the very, very low Coulomb interaction, which is the one, which is the case for graphene. And this is why, if we look at the band structure calculated for an angle which is not strictly the magic angle, but just very close to it to appreciate some weak dispersion here, and we think about tuning the electron doping or the hole doping in this system from this point to this point, what we would expect is very high resistances here and here and here, where we have physical gaps, but a fairly metallic behavior could be expected in between. But this has been shown is not actually the case. And actually, for integer fillings of the bands, we can see increase in the resistance. And this is a compelling proof of this of the relevance of electron-electron interaction in the system. And some kind of real space interpretation of this picture can be obtained looking at the distribution of the wave function in the system, accounting for the defined by the Moires generated by the two twisted graphene layer, because the wave function is mostly localized on one of the sides of the Moires, in particular the AA region. And then what we can imagine is that once we start to occupy these sites, it becomes difficult for electron to open different sides, and this is why we see high resistance. Now, what we tried to do in this study, it has been to experimentally observe these flat bands with ARPES. And the first challenge we faced, it has been the fabrication of suitable device for angle resolved emission spectroscopy. And the success of this experiment relied upon the extensive effort of the Hefedov group. Why are these samples so difficult to make when we want to study this crystal in ARPES? Well, this is because typically the way this twisted bilayer graphene is studied experimentally is when it is encapsulated top and bottom with thick hexagonal boron nitride layers. For ARPES, however, we need an open geometry because ARPES is a very sensitive surface technique, and we need to have access directly to the crystal without capping layer. Now, giving up on this capping layer is actually a huge deal, because first, this capping layer protects the crystal from pollution, for example, from air pollution when the sample is transported among facilities, but also because applying this capping layer can get rid of a substantial amount of fabrication residues that in our case might stay on the surface because of this of the missing capping layer, but most importantly because the capping layer is responsible for an increase in the structural stability and homogeneity of the sample, which means that even when the sample is carefully prepared, the preparation is never deterministic, so we never know exactly the twist angle of our graphene. But most importantly, we cannot know a priori from an optical image how extended is a region with a coherent twist angle. And so preparing these samples required tremendous efforts and lots of lot of red addition. But then when we need to study this, so this is why before studying this sample with the photoemission spectroscopy, we investigated them with low energy electron microscopy. This is an imaging technique that gives us information about the structure of our crystal, and in particular what we can see here, we can see several different regions just in this a small portion of the sample. And these several different regions, they look quite different. Most importantly, however, we can see that we have a grayish area here, which is fairly large, is definitely suitable for our measurement. And also the fact that we see a gray area here was a strong hint of the possibility of this being actually twisted bilayer graphene close to the magic angle. And this is because if we look at this other region here, where we can see these triangular patterns, what we know is that these triangular patterns, they originate from twisted bilayer graphene at very low twist angle. For such low twist angles, what is known is that the Moires cell is extremely large and is comprises either AB or BA stacked region. And the black and white triangle correspond exactly to this AB and BA region. The fact that here we see something that is gray, which is a combination of this black and white, is because we are not able to resolve the size of this triangle within this region. And this is because these triangles are much smaller than the one that we can observe. Given the size of the Moires cell of a magic angle twisted bilayer graphene, we were fairly sure that this was this could be a region with a twist angle very, very close to the magic angle. This is why then we brought this sample to the Electra synchrotron radiation facility to study it with photoemission spectroscopy. In photoemission spectroscopy, what we do is that we probe the photoelectron emitted with a monochromatic source from the crystal. We basically resolve the photoemitted electron and we split them according to the emission angle and their energy. And the intensity plot that we obtain is strictly related to the band structure of the system. as you can see here, the lateral size of the beam, which is submicrometric, is fairly, means that this area, which is few micron wise, is fairly suitable for our study. So what we do first thing when we start this kind of experiment is that we start to scan our sample in raster mode, up and down, and we collect the total signal to build an image which is a kind of duplicate of the optical image. And this allows us to navigate the sample, recognize the main feature, like the edges of the gold patterns, and finally locate the region of interest that we think might be twisted bilayer graphene. And in this region is where we performed our measurement. The first observation that I want to show you is a qualitative one. So what we did is that we started taking momentum energy cuts in this region of the reciprocal space where the K points of the two graphene layers are localized, and we started to cut along these lines and collect the photoelectron signal. And what is clear is that we can see mainly two strongly dispersive bands here, which are clearly related to the two graphene layers, but also what we can observe at the top near the Fermi level here is a weakly dispersive state that spans several mini-Brillouin zones. And this was the first evidence we got, the first direct evidence we got of these non-dispersive states. Then we tried to get a more quantitative understanding of the system. And what we did is that we compared our result with the theoretical calculation. These are tight binding simulated in the continuum model, with the continuum model. And what we can observe, of course, the first striking feature is that the calculated band structure has several spectral features that we are not able to resolve due to the spectral broadening of our experimental signal. However, the main ingredients, the main features are kind of well predicted, are in agreement with our prediction. So first, the dichotomy of the band on the left side, for example, here, while a more merged signal is observed on the right side of the dispersion, the presence at the Fermi level of the expected flat bands, and also a quantitative agreement, at least for the larger energy gaps which are induced by the interaction between the two graphene layers can be observed. So what we can see is that where we theoretically expect the larger band gaps, we can clearly see depletion of the experimental signal which are consistent with this observation. The last thing I would like to show is actually a very curious thing about RSEF. So when we study twisted bilayer graphene, what we need to remember is that we are studying a system which a priori is incommensurate. And an incommensurate system in principle should not show bands, and this is because we are missing the periodicity which is needed to define block states. One could argue that maybe for the peculiar twist angle that we have by accident a commensurate structure, but in that case something else is missing, and that is the backfolding of the bands. Backfolding means that if we look at the Brillouin zone of graphene, of single layer graphene, of the two single layers graphene, blue and red, we have a fairly large Brillouin zone. But the fact that the two are on top of each other should generate a Moires pattern, which is very large in real space, so very small in reciprocal space. And this should generate several mini Brillouin zones, and we should, in principle, we expect to see replica of these bands all around the reciprocal space. But this is not the case. And the way to see it is simply to start again with the linear chain and observe that if we, for example, calculate this band structure and then we add a potential as, for example, the periodicity of 4 unit cell or 20 unit cell or 100 unit cell, what you observe is indeed that the band structure is backfolded. But what we probe in RSEF is not strictly the band structure of the system, is more the spectral function weighted, the weight of the spectral function associated to each state. And what happens is we put this ingredient in our calculation. So if we actually get the we weight the bands according to their spectral weight, what happens is that adding a perturbation potential, which is fairly weak with respect to the interlayer potential, the band structure is indeed folded, but most of the spectral weight stays on the unperturbed band. And this is true no matter how much we increase the periodicity of the potential. What happens is that the more we increase the periodicity of the potential, the more extra feature we expect to observe. And this is indeed the case if we take, for example, constant energy gap. I'm sorry, I'm missing a label here. This is a kx direction in residual space, and this is the ky direction of residual space. The red lines, they draw basically constant energy contour of the band structure. And as we can see, this is indeed well spread all around the residual space. But the black marker, the black intensity plot shows us where most of the spectral weight is localized, which is better seen in this blue plot. So we can see that not all these states will contribute equally to RSEF. And indeed, if we look at these constant energy cuts, again, from our experiment, we see that they are much broader than what we would, that they are quite broad, so that we cannot resolve the fine structure of this system, but still we can see that qualitatively we recover a fairly good agreement with the calculation. With this, I would like to conclude my talk. I hope I showed you why it is fairly difficult to obtain high quality samples suitable for the emission spectroscopy. I hope I convinced you that we have direct evidences of observation of flat bands in twisted bilayer graphene with RSEF. And also I hope I convinced you that the fact that we don't see multiple replica of our bands is because of, it's actually not an answer, it's something that the technique that we kind of expect in RSEF. I would like to conclude thanking all the people involved in this project, in particular the people in the group of the University of Geneva that were extremely active in the RSEF characterization. All the people from the Hefetov group that put a substantial amount of effort in preparing this sample, and all the people in Leiden that thanks to low energy electron microscopy and scanning tunneling microscopy allowed to pre-screen the sample, figure out which one was the most suitable for RSEF, and basically sow the seed for the success of this experiment. And finally, thank you for your kind attention.
So thank you very much, Simone. So we already have questions. So there is a question by Johannes Lischner. So he asks what determines the distribution of a spectral weight? Whether is this an effect of the photoemission matrix elements?
Yeah, sure. No, matrix element, this is, I think that strictly speaking, this is not a matrix element effect in the sense that the way you calculate this spectral weight from tight binding is simply from the eigenvectors of the, associated to each eigenstate. So this is not exact. A matrix element effect is more is calculated within the transition, so it's not strictly matrix element. Matrix element needs to be plugged additionally to get better quantitative agreement, because in that case also polarization and cross-section effects are taken into account for. So this is simply spectral weight.
Okay. Another question from Bruno Amorin. He asked whether unclap replica due to the HBN substrate are observed.
No, in this case they are not, and this is because basically the presence of unclap induced by HBN depends on the orientation with between BN and twisted bilayer graphene. Now, what is known in the 2D material community is that when layers are close to mutual alignment, these effects are very relevant, which is why we made an active effort to to rotate the HBN 30 degrees away, the I-symmetry direction of HBN 30 degrees away from the I-symmetry directions of twisted bilayer graphene, so that all this additional Moires and Umklapp effect would not be there.
Okay, thank you. And Anmesh Gorai ask whether so which is the energy resolution in ARPES.
Yeah.
And also well, I asked the two questions, and also if the twist angle of the sample. So he says, okay, if the twist angle of the sample was not well known, then at what angle the theoretical calculation was done and matched?
So this is again the energy resolution of ARPES in this case is close to 50 milli-electron volt, which is why most likely why we see all this smearing of this signal. So we don't think that this is intrinsic or not necessarily just intrinsic of the sample. So 50 milliV is the reason why we see such broad signal and why we cannot see a neat dispersion, but actually something more smeared. The way we estimated the twist angle, it was actually a combination of it was mainly via STM. So with STM, what we can do is to measure this was done by the Leiden group. They measured the size of the Moires cell. And from the size of the Moires cell, you can estimate the twist angle with some accuracy. In our case, the estimation, it was between 1.34 and 1.37 degree. After that, the calculations were done. So it means that we did tailored calculation for this sample at this twist angle. And last question. Yes, also to some extent, LIM can give us upper and lower estimation of the twist angle, but mainly by STM.
Sorry, I have a question myself regarding to previous question. So in your experiment is energy resolution is 50 milli-electron volts. Now, in principle, which energy resolution could be reached experimentally? So somehow in the future, I mean.
At present, I think we are close to this. There are probably probably few beam lines that can do a bit better than this, but a conservative lower limit, I would say it's 10 milliV at the moment for this kind of a nano ARPES system. But to the best of my knowledge, I think this will change in the next few years, and there will be substantial upgrades.
Okay, thank you. And also there is a comment by Bruno Amorim. He mentions that so I think this is associated to a previous question. He says that the ARPES spectral weight, it's a photoemission matrix element, and he says that this is proportional to the Fourier transfer of the states, which essentially unfolds the band structure.
Yeah, let's say my only concern in calling it a matrix element is that at least when I think about a matrix element, I think about a coupling between bounded state and the free electron state via the photon, which is your perturbation. This to me is this is what I would call a matrix element. While what we calculate to give an estimate of this ARPES spectral weight is exactly what Bruno says is the Fourier transform of the states. So I was not comfortable calling it a matrix element because it doesn't require a transition in a sense.
Okay, so thank you very much.
You're welcome.
Now we move to the next speaker. So next speaker is José González from Instituto de Estructura de la Materia at CSIC in Madrid. And he will talk about marginal Fermi liquid in twist bilayer graphene.
Okay, so you can see the presentation now?
Yes, we can see it.
Okay. So first of all, I want to thank the organizers for the opportunity to give here this talk. I'm going to discuss a particular aspect of two-phase bilayer graphene, which has to do with the normal state properties. That is the properties of the normal state, the normal phase that is found above the superconducting dome. There have been experiments looking at the transport properties at this normal metallic state, in particular by the group of Pablo Jarillo, in which they have found this striking behavior, this linear behavior in temperature of the resistivity, which is quite remarkable. So this, in fact, is the kind of transport properties I would like to discuss. These properties are important because they are giving us information about the properties of the electron quasiparticles in the electron system. And in turn, from this information, we can get also some idea about the band dispersion and Fermi lines in the electron liquid. So let me begin by discussing band dispersions in two-phase bilayer graphene as we approach the magic angle. Well, the first thing I would like to stress is that these bands never become completely flat. And in fact, they develop quite interesting features. As you can see here, I am showing here energy contour lines in momentum space, where you can see, as I said, interesting features, in particular saddle points with a very interesting evolution. These are energy contour lines, so you can identify, for instance, the saddle points by looking at the crossing of contour lines, for instance, here. These saddle points are placed originally at the end point of the Brillouin zone, but as long as you are approaching the magic angle, they start moving, they deviate progressively from the end point, and at a certain critical angle, they double, they split in two, so there is a kind of doubling of the Van Hoff singularities in your system. And later on, they start moving towards the gamma K line, as you can see here. At a certain point, they give rise to an enhanced symmetry because, as you can see here, well, this is a single Ballet picture. So as you can see here, there is an enhancement of symmetry from C3 to C6. Well, this can be better seen. For instance, that the complete band structure is obtained obviously when superposing the left Ballet and the right Ballet in momentum space, and then you get this more complete picture. As I said, well, these black lines stand for energy contour lines. So again, we identify the saddle points by this crossing of the lines. And as you can see, at a certain point, there is this the doubling of the saddle points that are deviating from the gamma M line and approaching the gamma K line. And at a certain point, they merge. These couple of saddle points, they merge at the gamma K line. So for practical purposes, we can assign one of them to the first valence band and the other to the second valence band. Well, these are results obtained in the continuum model, but you can obtain a very similar picture computing in time binding approach. In fact, all the results that I'm going to show from now on are obtained in a time binding approach, in which I'm dealing with a Hamiltonian like this, for instance, when you have typically you have these matrix elements which are extended in real space with a typical exponential tail. And this gives rise in general to a very reliable picture of the low energy bands of graphene about the magic angle. Sorry, the two-phase bilayer graphene about the magic angle. If we compare the results from the continuum model and the time binding approach, we can see that there is a fair agreement. As I said, there is a point at which there is this splitting in two of the saddle points. They start then moving towards the gamma K line, and at a certain critical angle, they merge, they coalesce at the gamma K line, giving rise to a picture like this. You find then two different saddle points of Van Hoff singularities. One is in the first valence band, and the other is in the second valence band. And they have a quite different shape. In fact, the one that is contributing the most to the density of states is the one in the second valence band, because this is a Van Hoff, an extended Van Hoff singularity. So this is giving the dominant contribution. This is the important one, also contributing to transport properties. Now, applying this discussion to the problem that I want to deal with, that is this striking observation of the linear temperature dependence of the resistivity in this case, about half filling. This is the evolution. The red curve stands for the resistivity a little bit above half filling, and the blue curve is a little bit below half filling of the Moires superlattice. So you can see, obviously, this behavior doesn't fit in Fermi liquid theory, and cannot be explained either, for instance, invoking electron-phonon interaction, because electron-phonon interaction gives rise to a much stronger power law dependence, as you can see here, below the Debye frequency. So you could never explain this part of this low energy regime of the curve just invoking electron-phonon interaction. And this is why I'm going to turn to a discussion of an approach in which the interaction, the dominant interaction, comes from the electron-electron side. In this case, I have to pay attention again to the behavior of the dispersion and the Fermi lines of the system. And as I said before, the important saddle point, the important Van Hoff singularity in the system is the one in the second valence band. And this is because, well, you can see here, this is an extended saddle point. It's extended along the gamma K line. And Fermi lines that are close to the saddle point tend to develop these kind of straight segments, as you can see here. And these are very important for transport properties because they have a direct impact. For instance, when talking about electron hole susceptibility, the electron hole susceptibility has a very large peak when the Fermi line is placed very close to the saddle point, for instance, as close as 0.2 millielectron volts. It tends to develop this very large peak because the electron hole susceptibility is just a measure of the number of electron hole pairs that you can excite, and you can excite a lot of them with very low momentum just by crossing these straight segments of the Fermi line. So this has a very direct consequence, for instance, in the electron hole susceptibility. This also has a reflection in transport properties, like for instance, the transport decay rate. I'm going to compute in a semi-classical formalism of the Boltzmann transport theory. In this approach, the transport decay rate can be computed in this fashion. It gives us information about the decay of quasiparticles above the Fermi level through the emission of electron hole pairs. This is a transport quantity, which means that the electron hole susceptibility is computed here with this average of the Fermi velocities of the respective particles. The results that you obtain are shown here. When you are very close, when your Fermi level is very close to the level of this Van Hoff singularity, extended Van Hoff singularity, as close as 0.2 millielectron volts, you can see here that you reproduce this linear behavior of the transport decay rate. The different curves correspond to the continuous line. The continuous blue line corresponds to decay of quasiparticles from the second valence band. The dashed line corresponds to decay from the first valence band, and the dot line corresponds to a mixed decay from the second to the first, and vice versa. So you see that we get this linear behavior for the transport decay rate that is lost as soon as we depart from the Van Hoff singularity. When you place the Fermi level far away, then you obtain, of course, the non-quadratic behavior that is typical of Fermi liquid theory. Now, with this information, you can pass to the discussion of the resistivity. The resistivity is nothing but an average of the transport decay rate over momenta, weighted with the Fermi-Dirac distribution. So as you can see here, well, even at low temperatures, this resistivity can be computed just as an average over the different Fermi lines of your system. And in the case of when you are very close again to the level of the saddle point, you obtain actually linear behavior in this low temperature regime, there is a crossover temperature and then linear temperature again. This has to do with the fact that in this low temperature regime, your quasiparticles are preferentially attached to the saddle point. But if you increase the temperature, then you have the possibility of exciting quasiparticles from the Dirac cone that is right above the saddle point. So this is, in fact, this second linear behavior has to do with this typical behavior of quasiparticles decaying from a Dirac cone. And the Dirac cone provides a certain phase space reduction that is forcing actually this linear behavior. And once again, this is valid provided that you remain close to the saddle point. If you depart significantly, then you recover the quadratic behavior, which is typical of Fermi liquid theory. Now, these are transport quantities, but all of these have a counterpart also in the behavior of many body quantities, like for instance, the electron self-energy. You can compute the electron self-energy in the standard fashion as shown here. And now it shows again linear behavior now as a function of frequency. So this is just the counterpart of the previous linear temperature dependence. What is important also here is that this linear behavior, again with a crossover, for the imaginary part can be translated by using, for instance, the Kramers-Kronig relation, can be translated to find the behavior of the real part, and the real part develops this logarithmic correction to linear scaling of the self-energy. This is important because now with these two quantities, you can construct the electron propagator incorporating the linear decay rate and also finding this behavior for the quasiparticle decay rate. Sorry, the quasiparticle weight. That shows this logarithmic suppression at low frequencies. That is, we are in a system in which the quasiparticles are vanishing at the Fermi level. This is actually the hallmark of the so-called marginal Fermi liquid, which is a concept that was developed many years ago just to account for the behavior, for the phenomenology of the copper oxide superconductors. And it's a behavior that is now found also here when discussing the electron liquid for the metallic phase of twist bilayer graphene. Now, this marginal Fermi liquid should have also a reflection in thermodynamic quantities, like for instance, the entropy, because the entropy can be computed, depends directly on the real part of the electron self-energy. So you can show that this logarithmic correction is inherited by the entropy, so that it gets this logarithmic correction now at low temperatures. And this should have a reflection in quantities that one should be able to measure. For instance, the heat capacity, which is nothing but the derivative with respect to temperature of the entropy, also shares this logarithmic correction as a function of temperature. And even the thermal conductivity, which is given by the thermal diffusivity times the capacity, the heat capacity, should have this logarithmic dependence on temperature. Well, this is the discussion of this striking behavior. There is a second part that is even more difficult to explain about this behavior. That is the actual magnitudes of the resistivity and the transport decay rate, which is implied. These values of the resistivity are very large, and they imply actually a transport decay rate for quasiparticles that is entering the so-called Planckian regime. I mean, the transport decay rate of quasiparticles is so large that it can be obtained directly from the temperature times a constant of proportionality, which is just the inverse of the Planck constant. These values of the transport decay rate are very difficult to explain in any model. We have tried, and within this approach of the electron-electron interaction, we have shown that one is able to account for such large values in the Planckian regime by computing, for instance, with the long-range Coulomb interaction suitable screen with the RPA. So in this way, you can obtain values for the transport decay rate which are compatible with this Planckian regime, although obviously our predictions are not universal. So they have this drawback. But at least one gets this suggestion that one should be able, in principle, to account for these very large values of the transport decay rate in a model with just electron-electron interaction. So I think that I'm going to stop here. Thank you for your attention, and these are my conclusions.
So thank you, Jose.
Yeah.
I'm going to the questions. So there is already one question by Anirudh Chandrasekaran.
Yeah.
So it's asking, is equation 1, including the imaginary part of susceptibility, computed numerically? Does key diverge at mu equals 0 when the chemical potential is equal to 0?
The imaginary part of the susceptibility. Let me see.
Whether it is computed numerically, I think.
This one. Do you mean, I guess?
It is.
Well, yeah, I understand. Well, yeah. In the transport decay rate. Yeah, I know. Yeah, this has been computed numerically in a model with this particular dispersion and these particular Fermi lines.
Okay.
So these are results obtained numerically by computing this in a certain grid in momentum space, accounting for this dispersion, this particular extended Van Hoff singularity.
Okay, thank you. And Hector Ochoa asks, your computation of resistivity relies on Boltzmann transport theory and therefore on the existence of charged quasi-particles. But Hall measurements from Ohio State group challenges this picture. Comments?
Well, all my approach is a weak coupling approach. So certainly it's based on the existence of a Fermi line and of course quasi-particles that you can excite around this Fermi line. So obviously my approach is a weak coupling approach. So it starts by assuming that you may get certain quasi-particles in your system, but in this way, it's the same kind of assumption that was made in the original marginal Fermi liquid proposal. That again is something that is relying on the existence of something that resembles a Fermi liquid, although it has some deviations, but that you can tame in a certain way.
Okay. So thank you very much. So if there are no further questions, we go to the next speakers. That first we thank Jose.
Thank you.
Thanks. And the next speaker is Miguel de Jesus Mestre Gonzalez. He is from Universidad de Lisboa in Portugal. And he will talk about incommensurability-induced ballistic states in twist bilayer graphene.
Hello, everyone. First of all, thank you very much for this opportunity to talk in this very nice colloquium. So I'm going to tell you about our recent work that I did in collaboration. So I'm a PhD student, and I did this work in collaboration with my colleague Adi and also professors Bruno Amorim, Ruben Mondaini, Pedro Ribeiro, and Eduardo Castro. Let me start by making a very brief review on twisted bilayer graphene. So as you know, as we rotate the two graphene layers, we obtain these Moires patterns that I show you here in this animation. And for smaller angles, the size of these patterns becomes larger. And on top of this, there are some angles, which are the so-called commensurate angles, for which we can define a unit cell, a super unit cell, which can encompass these Moires patterns or not. But this is not general. So in general, we will have an incommensurate structure, and this is actually one of the most important concepts in our work. So just a brief historical review. Back in 2007, a continuum model for twisted bilayer graphene was developed, predicting the formation of the low energy Van Hoff singularities due to the interlayer coupling, and also a narrow band at the so-called magic angle, as you know. And this was experimentally observed back in 2010, and the discovery of superconductivity and correlated insulating phases boosted both theoretical and experimental research. And of course, this triggered many theoretical research, as we have seen in this colloquium, to try to describe the nature of these phases based on interactions. But what we did was to take a step back and ask to the single particle problem, okay, and ask if incommensurability is important. So we did this because incommensurability effects are often neglected in theoretical studies of this Ballet graphene, but we can also ask why should they be important at all? And the answer is that we also know that incommensurability can actually dramatically change the localization properties of a system. And a paradigmatic example of that is, of course, the one-dimensional Aubrey-André model, in which we apply a potential, quasi-periodic potential, which is incommensurate with the lattice. And as a function of the strength of this potential, we can have a transition between quantum phase transition between a ballistic and a localized phase. Now, this type of phenomena is not restricted to one dimension. It actually, several works have shown that this extends to higher dimensions. So we thought that this was a question worth asking. But now we run into the first problem, which is how can we study such effects in twisted Ballet graphene? Because we cannot just use Black's theorem and assume translational invariance. So a possible solution is to make the exact diagonalization of the tight binding model of twisted Ballet graphene. So, and that's what we implemented. So we considered this tight binding model that I show you here, which was already introduced and used in other references. And so the first term that I'm showing you here corresponds to the intralayer hoppings for each of the layers. And the second term contains the interlayer hoppings, where this T perpendicular depends on the distance between sites in different layers in an exponential fraction. And actually, we use the Slater-Coster parameterization that was introduced in this reference to describe this T perpendicular. Now, of course, with this approach, we can treat the model exactly, but we must work with finite system sizes, and therefore finite size scaling analysis needs to be carried out for an accurate study. Now, before showing you the results, let me first tell you about one important quantity that we use to probe localization properties. Let me stop just here at this point to tell you that I will only show you localization properties in momentum space, because in real space we found that the wave function was always extended as expected, and there were no significant differences in the localization properties. So what we use to probe localization properties in momentum space is this so-called momentum space inverse participation ratio, in which after we exactly diagonalize our model, we take the Fourier transform of the real space wave function for one of the layers, it doesn't matter which one, and we define this sum in terms of the absolute value of the normalized Fourier amplitudes, where this k is momentum and alpha is the sublattice index. Now, this quantity should scale in with some power of the system's volume. And depending on such scaling, we can distinguish between ballistic states, for which this exponent should be 0. And in this case, the wave function is localized in momentum space. So it's just a mixture of block waves, which is what we expect, for instance, for commensurate angles, for which momentum is a good quantum number. But we can also have these sub-ballistic states in which the wave function spreads in an extensive amount of k points, which means that as we increase our system size and therefore the grid of k points with which we are probing momentum space, more and more k points will contribute, and this quantity will scale in some way with the system's volume, which can be at most with the inverse of the system's volume. And in that case, we should be looking into diffusive states, okay? Now, having said this, I can go to the results, and let's follow this figure. So we start here in this figure A. What I'm plotting here is the density of states as a function of the angle and the energy. And as you can see, for larger energy, for our larger angles, there are these two energies for which the density of states is larger, which correspond to the Van 't Hoff singularities, and they eventually merge at around 1.1 degrees in this, forming this very narrow band. And the bandwidth becomes larger if we go to smaller angles. So of course, this is what was expected. What I want to say here is that no matter whether we take a set of commensurate or incommensurate angles, this picture doesn't change. So the density of, there are no significant differences observed in the density of states when we compare commensurate and incommensurate angles. However, if we look into the localization properties, that changes. So what I'm doing here to show you that is I'm taking this energy window bounded by these two dashed lines, and I'm computing the average IPR of k for all the states that fall within this window. And I'm doing this for a set of commensurate angles, which are these red data points that I show you here, and also a set of incommensurate angles, which are these blue data points. So there are different types of points here. So the darker the point, the larger it is the system size that we are using. In the case of the commensurate angles, you can see that the results are essentially system size independent, which is expected for ballistic states that should appear for commensurate angles. And also the IPR of k is not sensitive to the narrowband regime, which is around here 1.1 degrees. On the other hand, if you look into this set of incommensurate angles, you can see that the IPR of k becomes really small in the narrowband regime, and it actually scales down with system size, signaling here the presence of subballistic states. Now, if you move away from this regime, what you see is that the results approach the ones that we obtain for commensurate angles, and they become essentially system size independent, and therefore here incommensurability effects become unimportant. Now, we can do a more fine-tuned study and look at some angles around here, the narrowband regime. And that's what I'm doing here. So I'm picking some angles around 1.09 degrees, and I'm plotting here the density of states. And this, so we are seeing here density of states for this narrowband here. And what I want to do is to select some different energy regions and see how the IPR of k for the states therein behave. So for instance, if I select this energy window depicted by this shaded red area, an average IPR of k for such states, I obtain these results in here, which tells me that the IPR of k scales down with the inverse of the system's volume, or with L to the power -2, where L is just the system's length in each direction. Now, this could actually signal the presence of states with diffusive transport properties. However, if we move away from, if we go to other energies, for instance, this energy window that I show you here, we can see that even though the IPR of k scales down with system size, it scales down slower. So we can definitely claim that the incommensurability induces subballistic states at the narrowband, but they are not necessarily diffusive. Now, what we can also do is to move a little bit away from the narrowband. That's where in this plot I'm plotting this log plot of the density of states for a wider energy region. The narrowband is just this bit here now. And you can see that there are regions with very small density of states, and we can ask about the properties of such states. And if we compute the average IPR of k, for instance, for this window of states, we can see that it converges to some value with system size as expected for ballistic states, and their incommensurability effects become, again, unimportant. Okay. Now, in order to try to understand the influence of these ballistic states in transport, we computed the conductance by using the Landauer approach. So what we did was to consider two graphene leads coupled to a central region of twisted Ballet graphene, and this central region had a finite fixed width, and we varied the length of this region and studied how the conductance varied with this length, with system size. Now, the first thing that we did was to compute the conductance for the parameters used in the previous slide. But there we found that there were very severe finite size effects to draw any conclusion. And in order to try to mitigate or reduce these finite size effects, we use this trick of increasing the interlayer coupling around 4 times. So this is a well-known trick that shifts the narrowband angle to larger angles, in this case to around 4.4 degrees. And this reduces finite size effects because for a given system size, we will have a larger number of Moires patterns inside. Now, we can do the same exercise that we did in the previous slide, but now for these new parameters and find the narrowband regime. So here I'm plotting the density of states for an angle within this regime, so around 4.4 degrees. And now what I want to do is to compute the conductance for an energy within the narrowband and an energy outside this narrowband regime. And I want to do this for a commensurate and an incommensurate angle close to this for 0.4 degrees. So that's what I'm doing here in these figures. And what we can see is that for the commensurate angle, the conductance essentially converges to some value with system size, which is what is expected for ballistic states, okay? If we are looking at the commensurate angle, On the other hand, if we look into the incommensurate angle, we see that the conductance clearly scales down with system size as we increase it, signaling this presence of the subballistic states that we have found. On the other hand, if we move away from the narrow band and compute the conductance, for instance, for this energy equals to 0.06, what we see is that the results also seem to be converging with system size. On the other, and more importantly, the results are essentially the same if we consider the commensurate or the incommensurate angle. So here, as we have seen, the narrow band, the incommensurability effects become unimportant. Now, just one final comment in this slide, which is if you look into these smaller systems, we can see that the results are essentially the same for commensurate and incommensurate angles in the conductance. However, if you look into the exact diagonalization results, so if we do the same calculations that we did in the previous model, we can see clear signatures of subballistic states already for relatively small system sizes. So our conjecture is that even in the case that the narrow band occurs at around 1.1 degrees, the realistic case, we should observe signatures of these subballistic states in the conductance, but we should go to very large system sizes that we cannot do to computational cost. Okay, so just some brief conclusions. We have seen that the nature of single particle states is very different if we compare commensurate and incommensurate structures, and if we are in the narrow band regime. Now, we have seen that this incommensurability creates a subballistic states for which the wave function is delocalized in momentum space. And these types of states are concomitant with the decrease of the conductance with system size. And I didn't show you here, but also with non-Poisson energy level statistics. And finally, of course, this results in that the incommensurate nature of twisted Ballet graphene may be taken into account in perturbative studies of correlations, if we are looking at a narrow band regime.
Okay.
Thank you.
Okay, so thank you very much for this talk. Well, so any question can be put at the chat. So let me start asking question. You see that's a clear effect of this incommensurability. So now, normally when an experimentalist go to so look at the results, they know more or less the angle, mostly from the position of the doping at which they find the gaps for electron. So
the single particle.
The single particle gaps. Now, so if you have to say, okay, to an experimentalist, so they can be at angles which are twist angles which are close, like exactly. So this is in this kind of resistivity picture that experimentalists do. This sample is incommensurate, or this sample is commensurate. Can you give kind of feature that it will allow to distinguish clearly the incommensurability? I know that at present, so there is a kind of twist disorder, but if you could do it theoretically.
Yes. If one of the signatures for if the system was really commensurate would be the presence of this ballistic transport. However, in my view, I think a generic sample will be incommensurate. So it's because to have a commensurate structure, it will require like an infinite amount of fine tuning. What we can be is we can be very close to a commensurate structure, and perhaps in that case we can see a typical behavior that can be close to these ballistic-like, but I think in general we will have an incommensurate structure.
Okay, thank you. So from the chat, Unmesh I ask, where is the incommensurability accounted in the modeling? And,
yes, that's it.
Okay, so
sorry.
Two questions are asked, and so I will ask the two if you don't mind, and then the other one is, As for the angles where twist bilayer graphene is commensurate, have you matched the commensurate versus incommensurate calculation that they are the same?
That's a very important question, which is how do we simulate these incommensurate structures? And so it's important to define what we mean by commensurate here. So an incommensurate structure is a system where the system size is just a single unit cell. So the supercell of the system is the system size itself. A commensurate structure, on the other hand, is a structure in which we have multiple unit cells inside the system. Okay. So for the commensurate structures, we increase the system size up to where there is convergence, and then we no longer have to increase more the system size. But for the incommensurate structures, as we increase the size, we always guarantee that there is a single supercell in the system, so that the system is always incommensurate. So I think this more or less answers both. No?
Okay. Yeah. Well, I think so. So then there is another question by, so the Unmesh Gorai, it's also happy with the answer. So Tobias Stauber asked, Bistreeter and McDonald show that the continuum model holds independent of the incommensurability. This suggests that you should see no differences for small angles, theta smaller than 1 or 2 degrees. Why do you still assume differences?
No, this is an important thing. So if you look at the spectral properties, that's what I've shown, they are essentially the same. So if you look only at the density of states, for instance, it doesn't really matter if you use commensurate or incommensurate structures. What we are seeing here is that if you look into these, let's say, wave function properties, or even into the transport properties, there can be drastic differences, even at the single particle level, if we compare commensurate and incommensurate structures. So yeah, there is a difference. That's what we are showing. Yeah.
Okay. So thank you very much.
Thank you.
Okay. And so we now move to the last session of this morning. So it's given by Hector Ochoa from Columbia University. And he will talk about the strain-induced excitonic instability in twist bilayer graphene.
Okay, yeah, thank you, Lene. You can see my screen, right?
Yes, that's perfect. Yeah.
Okay, thanks. Yeah, so I'm gonna spend most of my time actually motivating the work rather than going into some of the details that I mentioned in my abstract. But of course, at the end of the talk, you can ask questions, or you can shoot me an email to my address. Okay, so yeah, now it works. Yeah, so I'm going mainstream here, and I'm showing the a slide that most people use to introduce this topic. So on your left, you have the original results by the group of Pablo Faria at MIT. And on the right, you have a phase diagram of strongly correlated system, in this case, Cooper superconductors that I took from this review article. But actually, what I would like to do in this talk is to emphasize the difference between these two types of systems, and in particular, aspects that are related to questions that appear in the literature from time to time. So, for example, which is the role of phonons and these Moires, which are the source of disorder, and related to these two questions, which is the effect of a strain or heterostrain, the strain accumulated between layers in the electronic properties of this system. And the first point I wanted to make is that all these strongly correlated systems, Cooper, ignitite, heavy fermion systems, are more or less crystalline solid state systems, whereas twisted bilayer graphene and Moire materials in general are something in between a solid and a soft matter system, in the sense that they generically form incommensurate lattices, which are only quasi-periodic. Okay. So, for example, associated with this incommensurability, there are new soft collective modes that are called phasons that can be naively understood as the sort of the phonons of the Moires superlattice, if you wish, and are related to the fact that now when we slide one layer with respect to the other, that generates energetically equivalent configurations of the system, because in a commensurate system, the system is already exploring all the possible stacking configurations, which is what I'm trying to represent with these figures. Now, when you go to small twist angles, there are, well, virtually no difference between commensurate and commensurate structure, or for the last talk challenge this statement. And this is something that we usually exploit in our theoretical modeling and these so-called continuum models. And now the problem in that case is that lattice relaxation effects are important. That means that the system tends to expand the regions of partial commensuration to the expense of creating solitonic objects, stacking domain walls, where strain is either concentrated or relieved. And in that case, we still have this phase and mode, but cannot be straightforwardly identified with the read motion of one layer with respect to the other. These modes correspond or describe more complex atomic rearrangements describing the sliding motion of these solitonic objects. Now, also another comment I wanted to make is that you can actually create these strain solitons at will if you are able to control the amount of strain in your sample. And this is something that Drew Edelberg, a former students in the group of Abhay Pasupati here at Columbia, did. So they have this type of devices. The material was molybdenum diselenite, and you see that so they have several of these samples in which so the sample was attached to two piezoelectric towers that control the amount of tensile strain applied to the system. And as you can see here, the topmost layer in many of these devices was actually detached from the piezoelectric, so it only felt the strain through the van der Waals interaction with the rest of the material. And these topographic STM images illustrate actually what happens. So at the beginning you apply a strain and nothing happens. Nothing means that the first layer wants to be commensurate with the rest of the system, but eventually at certain critical strain that corresponds roughly to 1.5%, these kind of solitonic objects are created, which correspond to these white features in the topographic image. And these features that correspond exactly to a misfit of one lattice constant, so it's a discommensuration of one lattice constant. This increase in density as you increase strain. They can go to up to 3% of strain. And this process is completely reversible. So actually, this is a almost textbook example of a commensurate transition driven by strain, where this critical strain is going to be given basically by the competition between the two relevant energy skills in the problem. So B corresponds to the difference in free energy between the different high symmetric stacking configurations, and these are, of course, the Lamé coefficients of this first layer. And actually, you put numbers here from DFT, and actually agrees pretty much very well with the experimental observation. Okay, so there are many interesting aspects about this work, and you can check the details here in the reference. So one thing that probably you notice is that actually the experiment doesn't look exactly as these schematics, because these domain walls break into multi-strike domains. And this is, we believe, pretty much associated with the presence of disorder in the sample. Actually, these soliton crossings are a very interesting object because they always appear in pairs. And one of these crossings, that precisely the one that corresponds to a stacking of the selenium atoms sitting on top of each other, those are very efficient traps for electrons, so they behave as a quantum dot. But the maybe the aspect that I wanted to emphasize with this slide is that, as we have seen, a strain between the layers actually stabilize an incommensurate configuration as the ground state of the system. Okay, so this is a list of other differences between crystalline and incommensurate system, one point I wanted to emphasize is the sensibility of the Moire pattern to disorder, which is partially due to the formation of these solitonic objects, but more fundamentally due to the different nature of the Moire superlattice itself. So this is exactly what I'm trying to represent with this figure. So imagine, for example, that you have some defects in a graphene lattice here. So let's imagine that these are representing vacancies, for example. So these vacancies are not going to break the long-range crystalline order of your lattice. However, and basically because the vacancies are embedded in the lattice itself. But this is different in a Moire system because now, if you see animation, if you slide one layer with respect to the other, the position of the vacancies with respect to the Moire superlattice is changing. So that means that these vacancies break the translational symmetry of the Moire superlattice, and they're gonna pin these solitonic objects, just according to general Imprima arguments. Okay, so that's one observation. The other observation is that twisted samples, or at least the idealized version of them that we theoreticians have in mind, are not the true ground state of the system, are only metastable. So a relaxed structure is only metastable in the sense that it's not the true ground state, the true minimal energy configuration in the system, unless there is some agent, like for example, strain in the previous slide, that stabilize this relative alignment. Okay. Okay, so after this long introduction, this brings me to actually the problem that I wanted to address in my talk, which is the disparity in transport behaviors, in particular at the neutrality point, between different devices of twisted Ballet graphene. So here in this table, I tried to summarize, which is the different behaviors of these different devices from different groups. So the renal samples from MIT, Columbia, and UCSB were superconducting, but not insulating at neutrality, were only semi-metallic. There are samples or devices that seem to be in which the twisted Ballet graphene seems to be aligned with the encapsulating boron nitride, and those are samples that are not superconducting but display sometimes quantized anomalous Hall effect, typically a 3/4 filling of the conduction band. That's, for example, samples from Andrea Jan that are also insulating at neutrality, but that gap can be explained in terms of this alignment with boron nitride. And finally, we have samples from IFO, from Dimitri Efetos's group, that are very homogeneous. There are no signatures of particular alignment with this boron nitride. This homogeneity is sort of manifested in these enlarged superconducting domes that you can see here in the density plot. And these devices are also insulating at the neutrality. And maybe the most striking thing that maybe sometimes people don't emphasize is that actually, according to these these RNU plots, this insulator neutrality is the strongest one. It's the one with the largest transport gap, which is about 10 Kelvin, I believe. So now the question is, why the best developed insulator in some uniform samples are not observed in other devices, which is kind of counterintuitive. And this is kind of the question that I had in mind when I started thinking about this. Okay, so what does theory tell us? Okay, so there are many already, for example, Hartree-Fock calculations in the literature. Probably Tommaso elaborate more on this. Unfortunately, I skipped your talk, Tommaso, so I was still in bed. And basically, all these studies show that for relative moderate strength of the Coulomb interaction, a gap at neutrality is open in the system. The simplest way to understand how a gap is open is because the ground strength of the strings in the presence of long-range Coulomb interactions breaks spontaneously some of the emergent symmetries of long Moires superlattices that protect the existence of Dirac points in the band structure. So basically, the associated order parameter hybridize the electron and hole branches of these Dirac points. So that's why you can understand all these forms of orders as some sort of excitonic order. And of course, there are different possibilities. So you can break the so-called C2T symmetry, which is a fancy way to say that charge tends to be accumulating more in one sublattice than the other. And of course, there are different possibilities because now you have 2 layers. Or you can, for example, break the Ballet symmetry, the separate conservation of charge on each Ballet sector by hybridizing these microscopic values. And the thing is that all these numerical solutions for the ground state seem to be very close in energy, which means that the particular conditions of the sample are probably dictated which kind of order is dominating here. Okay, so more technical comment that I wanted to make is that in addition to these emergent symmetries that the continuum model naturally incorporates and protect these Dirac points, these models also have some additional approximate symmetries in certain regimes. In particular, at the small twist angles, you have an approximate particle-hole symmetry that relates electron and hole states at opposite points of the brilliant zone that are implemented by these kind of anti-unitary operators. So here, these are Pauli matrices acting in layer and sublattice. Now, if you combine this anti-unitary symmetry with time reversal, the other anti-unitary symmetry in the system, you can define a chiral unitary symmetry that is now given by this operator. And this chiral symmetry is different than the symmetry that appears in the so-called chiral limit of the continuum model that corresponds to neglecting interlayer hopping in AA stack regions. Okay, and this symmetry actually plays an important role in my study. Of course, the other important character is heterostrain. So let me. I'm going out of time, or
yes.
Okay.
Ready.
So I'm going to conclude with this slide actually. So the idea is that what does heterostrain does? So heterostrain shifts the Dirac points both in momentum and in energy. And basically creates this kind of Fermi surfaces with maximum overlap between the conduction and the valence band. And this Fermi surface is generically unstable against the condensation of electron hole pairs. And as the figure suggests, this kind of excitonic order breaks the Ballet symmetry and actually also breaks time reversal symmetry. So the order parameter describes or corresponds to Kekulé-like interlayer currents. Okay, so that's basically that. And the other comment is that this excitonic state is very sensitive to potential disorder or deviation from a uniform heterostrain profile, because basically it has the same effect of magnetic disorder in a superconductor. So once you break this particle symmetry, you lose this electron hole nesting property of the Fermi surface. So this brings me to the conclusions. Sorry for extending my time.
Okay, so thank you very much, Hector. So let's see if there are questions from the chat. So I will start asking a question. So what you mentioned is the impact of heterostrain on this excitonic instability. Now, homostrain will not give any, will not have any impact in this.
Sorry, say again.
So heterostrain, so what you mentioned is the effect of heterostrain.
Yes.
But almost, so it's this strain equal in both layers. Yeah. Will be will also have an effect, or?
No, because so is heterostrain what really matters here, because it's heterostrain what controls this electron hole nesting of the Fermi surface. So let's say that same amount of strain in the two layers will sift the cones, the blue and red cones that come from opposite values in the same, let's say, direction, right? So you are basically in the same situation you were before. Now, heterostrain is what really sifts these cones in opposite directions. Okay, so that's why deviation from this heterostrain profile actually is going to reduce the condensation energy of this excitonic state, and that's why it's so sensitive to the disorder. On the other hand, is heterostrain what is going to tend to stabilize, and that's kind of my claim or the hypothesis, the relative alignment between the two layers.
Okay, so what is key is to have the Dirac points at different energies.
Yeah, so anti-correlations of the strain in the two layers.
Okay, so there is also a question by Tobias Stauber. So he asks whether this can be seen as an effective in-plane magnetic field.
Yes, so you have both effects. So if you have a heterostrain profile that breaks C3 symmetry, the Dirac cones are going to displace in momentum away from the mini Dirac point or the renal coordinates of the Moires and so on, and that can be described in terms of a Salo gauge field. But now you have this additional effect of the shift of the energy of these Dirac cones that is like is new with respect to what you will have in graphene, let's say.
Okay. So thank you very much. So thanks. Well, thank you. But then before leaving, just please two announcements. One is don't go yet. So just switch on your cameras, all of you. We're going to take a group photo. And the other one is this afternoon at 5, we have the special session of the symposium. We will have both the poster presentation. So first there will be flash talks. I will especially ask all the speakers of this morning to be there in order to have, after the flash talks, general discussions where people can ask more questions to the speakers of this morning. In fact, we will have the micros open, so that will make it easier. And also, so there will be the possibility to have breakout rooms to in such a way that people even can have also, let's say, private discussions or poster discussions in the usual way, more in small groups. So just that's all. So let's.
Okay, so I'm going to take the picture now. So everyone smiles. Cheese. Good. Okay, thank you.
So thank you and see you this afternoon.